the regenerative cycle. Another important variation from the Rankine cycle is regenerative variation of from which uses feed water heater. The basic concept of this cycle can be demonstrated by considering the Rankine cycle without superheat as shown in the picture. There is a Rankine cycle without superheating at point 3. There is a saturated vapor. During the process between state 2 and 2 prime, the working fluid is heated while in the liquid phase. So we have liquid, superheat, steam, and two phase. The working fluid heated to the liquid phase, and the average temperature of the working fluid is much lower than during the vaporization from 2 prime to 3. Average temperature, the average at 2 prime is lower than T the average T between 2 prime to 3. The average temperature that comes from 2 to 2 prime. The process between state 2 and 2 prime caused the average temperature at which heat is supplied in the Rankine to lower than the Carnot cycle. T average lower than also T average Carnot cycle 1 prime to Carnot, and as a result the efficiency of the Carnot, the Rankine, much smaller than the efficiency of the Carnot cycle. In the regenerative, efficiency of Rankine cycle is lower than the corresponding Carnot cycle. In the regenerative cycle, The working fluid enters the boiler to increase T average at 2 to 2 prime process. Consequently, the average at which heat is supplied is high. At Q in is high. So efficiency increases. For more discussion, consider the first and ideal as regenerative cycle as shown in the next picture. In this picture, the unique feature of this cycle compared to the Rankine cycle is that after leaving the pump, the liquid circulates around the turbine case, counterflow to the direction of vapor flow in the turbine. Thus, it is possible to transfer to the liquid flowing around the turbine the heat from the vapor as it flows through the turbine. This area compared to cycle Rankine cycle, the liquid water, liquid at point 2 goes around turbine case, and the water flow to the direction of the vapor flows in the turbine. Thus, it is possible to transfer the liquid flowing around the turbine the heat from the vapor. Goes to the liquid and T average in this cycle to prime increase. Let us assume for the moment that this is a reversible heat transfer. That is that at each point the temperature of the vapor is only infinitesimally higher than the temperature of the liquid. In this instance, the line 4 to 5 on TS diagram, which represents the state of the vapor flowing through the turbine, is exactly parallel in the line 1, 2, 3, which represent the pumping process 1, 2, 2, and the state of liquid flowing around the turbine. Consequently, the area 2, 3, BA2 2, 3, BA2, this shaded area, and the 4, 5, DACD are not only equal but congruous, and these areas respectively represent the heat transfer to the liquid and the vapor from the vapor. From the to the vapor. Heat is also transferred to the working fluid at constant temperature. Heat also transferred to the working flow. At T constant, shown in this line. In the process 324 and the area 34 dBA represent the heat transfer. Heat is transferred from the working fluid in process 5A, and the area represent the heat this heat transfer. We are talking about the areas 3, 4 dBA3, 3, 4 dBA3 heat in, and this area Q out. This area is exactly equal to the 1 prime 5 prime dBA y prime. Let me provide the picture again. Y prime 5 prime dB 1 prime. Which is the heat rejected in the related Carnot cycle. Thus, the efficiency of this idealized regenerative cycle is exactly equal to efficiency of the Carnot cycle with the same heat supply and heat rejection temperature. The efficiency of regenerative branching equals to the efficiency of the Carnot cycle with same temperature and pressure, for example. Obviously, this idealized regenerative cycle is impractical. Idealizedly impractical. First, it would be impossible to effect the necessary heat transfer from the vapor in the turbine to the liquid feed water. Furthermore, the moisture content of the vapor leaving the turbine increased considerably as a result of the heat transfer. The disadvantage of this was noted previously. The practical regenerative cycle extracts some of the vapor after it has partially expanded in the turbine and uses feed water heaters as shown in the next picture. The next picture is the previous cycle. Increase the moisture of water after we transfer in the turbine, so to avoid feed water heater use. Furthermore, the moisture content of the vapor leaving the turbine increased considerably. The advantage was noted previously. In the feed water addition in the cycle, we have steam entered the turbine at area of 5, this point. After expansion to state 6, some of the steam is extracted and enters the feed water heater, this equipment. The steam that is not extracted is expanded in the turbine at point 7 and is then condensed in the condenser and goes from point 1 to this condensated is pumped into the feed water heater, where it mixes with the steam extracted from the turbine. The proportion of the steam extracted is just sufficient to cause the liquid leaving the feed water heater to be saturated at stage 3. Note that the liquid has not been pumped to the boiler pressure, but only to the intermediate pressure corresponding to a point C6. It means that intermediate pressure to the stage C. Boiler pressure the liquid has not been pumped to the boiler pressure. The liquid has not been pumped to the boiler pressure P3 or P4. This is P5, but also on intermediate to P6. Another pump is required to pump the liquid leaving the feed water heater to the boiler pressure as shown in the picture. This pump The significant point is that the average temperature at which it is supplied has been increased. T average increases. Consider a control volume around the open feed water in this picture. We have these relations. For the continuity, we have feed water 0.6, 0.3 and 2, and 0.2 continuity. Equations say that N2 plus N6 M dot 3 satisfy with the extraction fraction as M dot 6 on M dot 5 M dot 5 entering the turbine M dot 7 we have a turbine M dot 5 6 7 M dot 7 M dot 5. Which is also M dot 1, M dot 2. For the first law, we have these relations. M dot 2H2 plus M dot 6H6 will be equals to M dot 3H3, into which they substitute the mass flow M dot 3, M dot 5. We have this expression as Y M dot 5 H5 H2. M dot 5 H6 M dot 5 H3. Okay, now we have this relation for the feed water heater and the system M dot 2 plus M dot 6 M dot 3 y equals to M dot 6 on M dot 5 M dot 7 M dot 5 dot 2 M dot 1. And also we have from first law M dot 2H2 plus M dot 6H6 M dot 3H3. And also we have M dot 3 equals to M dot 5. We can simplify this M.5H2 Y M.5 H6 M.5 H5. We take state 3 as the limit of saturated liquid. And then solve the parameter pi, which was M6 on M.5. The portion of the working fluid goes to the feed water heater. This is established the maximum extraction fraction. We should take out this extraction pressure. This cycle is somewhat difficult to show on this diagram because the masses of the following through the various component vary. The area 4, 5 CB4, 4, 5 CB4 represent the heat transferred per kilogram of working Q in. But since not all the steam passes through the condenser, the area 17 CA 17 CA represent the heat transfer per kilogram flowing through the condenser. Q out condenser, which does not represent the heat transfer per kilogram of working fluid entering the tube. Between stage 6 and 7, this only part of the steam is flowing through the turbine. The example that available in the example solution part. Up to this point, the discussion and example have tacitly assumed that extraction, steam and feed water are mixed in the feed water heater. The extraction, steam and feed water are mixed in the feed water heater. Another frequently used type of feed water heater known as closed heater is in which the steam and feed water do not mix. Steam and feed water rather, heat is transferred from the extracted steam as it condenses on the outside tube, which the feed water flows through the tubes. In a closed heater, a schematic sketch of which is shown in the picture in the next page. Closed heater. Closed heater. The condenser may be pumped into the feed water line, or it may be removed through a tap to a lower pressure heater or the condenser. Feed water, a trap, and alternative case. Let us analyze the closed bit of water in this picture. When a trap with a drain to the condenser is used, we assume we can heat the feed water up to the temperature of the condensing extracting flow, that is T3, T4, also T6A. Temperature of condensation extracting flow. As there is no drip pump, conservation of mass, say that m.4, m.3, m.2, m.5. I'm looking for m.5, which is in the turbine after boiler. And also m.6, y.m.5, extraction steam from the turbine. M.6c, the other flow. We have two flows. This flow comes from continuity, and from First law we have this relation m.5 H2 plus y.m.5 H6 m.5 H3 plus y.m.5 H6A. In fact, it is come from m.2 H2 plus m.6 H6 m.3 H3 m.6A H6A, and with simplification with the relation we receive to this equation, which we can solve for y as H3 minus H2 H6 minus H6A. Open feed water heaters have the advantage of being less expensive and having better heat transfer characteristics than closed heat water. Open heat water are less expensive and better heat transfer characteristics. Than closed feed water heater. They have the disadvantages of the requiring a pump to handle the feed water between each heater. In many power plants, a number of extraction stages are used, true rarely more than 5. The number is of course determined by economics. It is evident that using a very large number of extraction stages and feed water heaters allows the cycle efficiency to approach that of the analyzed regenerative cycles, where the feed water enters the boiler as saturated liquid at the maximum pressure. The practice, however, this cannot be economically justified because the saving effect by the increasing inefficiency would be more than offset by the cost of additional equipment. A typical management of the main component in the actual power plant is shown in the picture in the next page. Note that one open feed water heater is the accelerating feed water heater. This heater has deaerating feed water heater. This equipment. This heat water has the dual purpose of heating and removing the air from feed water. Heating and removing the air from heat water. This heater excessive corrosion occurs in the boiler unless excessive erosion occurs in the boiler. Note also that the condensate from the high pressure heater drains to the intermediate heater and the intermediate heater drains to the decreasing feed water heater. Intermediate pressure heater and the intermediate heater drains to the decreasing feed water, deaerating the heat water plus deaerating feed water heater, condensate. Condensate the water. Many actual power plants combine a reheat stage with a number of extraction stages. The principle already considered are readily applied to such a cycle.